I welcome all to this lecture on HVDC systems. Today we are going to discuss protection schemes. I'll write here protection schemes for HVDC system. This is our topic of discussion today. In our last lecture, in fact last 3 lectures, we have been discussing various maloperations in HVDC converters, and we discussed about arc through, we discussed misfire and also commutation failure. These 3 maloperations are frequent, and among these 3 maloperations, in fact, commutation failure is very frequent. And we have tried to draw the waveforms for all these types of maloperations, and we have seen that the normal sequence of conduction of valves changes whenever there is any one of these maloperations, and for a significant period of time the load voltage becomes 0. And in case of inversion mode of operation, for example, for some period, some small period, the load voltage also becomes positive. And similarly, you have seen in previous lecture in double commutation failure, load voltage remains positive for an appreciable period of time, and average load voltage is nearly equal to 0. Now these maloperations have to be taken care of by the controller in HVDC systems, and these maloperations also result in certain problems in the operation of converter. Now let us try to discuss some protection schemes for HVDC systems. Now before we discuss protection schemes of HVDC systems, we must be aware of what are the desirable features of protection scheme. I will write here desirable features of protection scheme. Any protection scheme which we are using for an HVDC system, it should fulfill certain desirable features. What are those desirable features? Number 1, the protection scheme should be selective in nature. Selective means that the protection scheme should operate only for that zone or apparatus for which it is designed. Okay, it should not operate for a fault which is outside the zone. This can be explained with the help of this simplified diagram. Let us suppose this is line 1 and this is line 2. I am showing parallel feeder system. And let us suppose we have a protective system here. And let us suppose fault occurs in line number 2. The protective scheme should be selective, means your protection which is installed in line number 1 should not operate for any fault in line number 2. Okay, so it should be selective. It should protect only those equipments and the line in which it is placed. Similarly, if you have a protection scheme on line number 2, it should operate only for those faults which occur on line number 2. It should not operate for faults on line number 1. So this is what we mean by that protective scheme should be selective. This is first desirable feature. Second desirable feature is it should be discriminative in nature. Discriminative. Discriminative means, a fault results in the increase in the current. An overload also results in the increase in the current. But your protection scheme should be designed in such a way that it operates only for fault, not for overload. The fact is that the current level increases in both the cases, fault as well as overload. But your protective scheme should be discriminative. It should discriminate between fault and between fault and overload, and it should operate only for fault conditions, not for overload conditions. So this is what we mean by it should be discriminative. Third is it should have high speed. The protective scheme should be operating at high speed. This means, generally the notion is that whenever a fault occurs, your protection scheme should clear the fault at a very, very high speed, almost in no time. If that is the case, that means if the operation or if the action of protective scheme is very, very fast, Then it may operate for transients also. Transients are temporary, these malfunctions. Whenever a transient occurs, their transient may be there for a few milliseconds, a couple of milliseconds or so, or even less than that. So if our protection scheme is very, very fast, then it may operate even for transients, and that is not desirable. It should operate only for faults, not for transients. So therefore, we can say that our protective scheme should be high. It should operate at high speed. It should be quick, but not, it should be quick enough, but not as so quick that it should not be so quick that it operates for transients also. So therefore, when you design a protective scheme, you have to take care of this fact that it should operate only for faulty conditions, not for transients. No doubt, protective scheme should be fast enough, but not so fast that it operates for transients also. Okay, this is third desirable feature. Fourth is that your protective scheme should be reliable. It should not be like your protective scheme operates for a fault, and when second fault occurs, it does not operate. And when third time fault occurs, it operates. And when fourth time fault occurs, it does not operate. It should operate for all abnormal conditions, and it should be reliable. Its reliability level should be very high. And fifth desirable feature is that it should have backup protection also. Your primary protection should be aided by backup protection, which means if primary protection fails, then there is still backup protection which will provide protection to the system. So these are some desirable features of protection schemes which you design for Hvdc system. The protective scheme should be selective, it should be discriminative, it should operate at high speed, it should be reliable in nature, and it should be provided with backup protection. So these are the desirable features of protection scheme or protective scheme. Now, your Hvdc system comprises of, it has AC side and it has DC side. So therefore, you have to provide protection for both sides, AC side protection as well as DC side protection. Let us first of all discuss protection of AC system. Now you have to provide protection of AC system against various abnormalities, like you have to provide protection against overvoltage. I will write here. You have to provide overvoltage protection, and you have to provide overcurrent protection also on AC side. Overcurrent protection. Now if you take overvoltage protection, okay, let us take overvoltage protection first. Now, before you design a protection scheme for overvoltage protection, you must know what are the causes of overvoltage on the AC side of the Hvdc system. Causes of overvoltage. There are very well-known causes of overvoltage on the AC side of your Hvdc system. First is, we can say, switching. Okay, capacitor switching or inductor switching, it results in overvoltages. Second cause is lightning stroke. Lightning stroke. Since your transmission lines are exposed to atmosphere, okay, and your AC system is exposed to atmosphere, it may be hit by a lightning stroke. And whenever there is a lightning stroke, that results in large overvoltage on the system. And third major cause is LG, that is line to ground fault, raising voltage of other lines, voltage of other lines or other phases. If you have a three-phase transmission, you have a three-phase system, if line to ground fault takes place and if neutral is not properly grounded, then the line to ground fault on one phase will raise the voltage of other phases, healthy phases, and that causes overvoltage. So these are the main causes of overvoltage on the AC side of Hvdc converter. Now, how to provide protection? Okay, overvoltage protection. How to provide overvoltage protection against these causes? Overvoltage protection can be provided by overhead ground wires, Okay, you have overhead, your transmission tower carries an overhead ground wire, a wire which is grounded, and whenever a lightning strike is there, the energy of lightning strike is arrested by this overhead ground wire and it is grounded. Okay, second is by providing what we call as protective gaps, and third is by providing lightning arrestors. I will write here lightning arrestors. Now, as far as these protective gaps are concerned, I can show you the protective gap like this. This is an AC system. This is the schematic diagram of protective gap. This is the symbolic representation of protective gap. There is a gap between these two. Whenever an overvoltage occurs on, say, this line, okay, because of any of the above causes, because of line to ground fault on other phase, or because of lightning strike, or because of inductive or capacitive switching, the overvoltage ionizes the air in this gap. So in this gap there is air. That air gets ionized, and once the air gets ionized, so all the energy it's grounded through this, because this protective gap is grounded, so all the energy or the voltage is grounded, and that protects your line or your AC system from overvoltage. But the problem with this protective gap, I will write here PG. PG means protective gap. The problem with this protective gap is that once the overvoltage, energy due to overvoltage because of ionization of air in the gap is grounded, then when normal voltage is restored, the gap still remains ionized. That means it grounds the normal voltage also. It grounds the system under normal voltage operation conditions also. So to deionize the gap, you have to increase the gap. Okay, there is an arrangement, a mechanical arrangement by means of which, if this is your normal gap, so you have to increase the gap under normal operating conditions. When you increase the gap mechanically, so the air gets automatically deionized. So to deionize the gap at normal voltages, you have to increase the length or the spacing of the gap. Okay, the area of the gap you have to increase, and once the gap is deionized, then you restore the normal gap. Okay, that means this is problematic thing, because whenever an overvoltage strikes your AC system, the gap is ionized and it grounds the energy associated with overvoltage. Fine, yahan tak to theek hai, but then when normal voltage is restored, the gap still remains ionized, which is undesirable. Therefore, to deionize the gap has to be increased, okay, which is somewhat problematic. So therefore, instead of using protective gaps, the practice is to use these lightning arrestors. This is LA. LA means lightning arrestor. Now, lightning arrestor comprises of a nonlinear resistor. Lightning arrestor comprises of, I will write here, nonlinear. It exhibits a nonlinear resistance. Nonlinear resistance means at high voltage, this lightning arrestor, it presents very low resistance, and at low voltage, it produces very high resistance. That means when there is no overvoltage, normal voltages are there, the lightning arrestor will have high resistance. So no energy will flow through this. And whenever an overvoltage occurs on this AC line or AC side, so the resistance almost drops to zero, and all the energy which is associated with overvoltage, that is grounded. Okay, so you don't need to increase the gap for deionization, etc. So that problem is automatically solved. So these are two very commonly used three commonly used protective schemes for providing overvoltage protection. First is, as I have written here, overhead ground wires. This is normally used for transmission line protection. And second is protective gaps. This is the protective gap. And third is lightning arrestor. So this is how overvoltage protection is provided to AC system. What about overcurrent protection? If I write here overcurrent protection, OC protection. Overcurrent protection is provided by fuses. Like many equipments are fitted with fuses for providing overcurrent protection. Then relays, circuit breakers, and current limiting reactors. Current limiting reactors. Okay. When an AC equipment is fitted with a fuse, as soon as there is overcurrent because of, say, some short circuit, the fuse blows and it protects the equipment. Similarly, you may have relays and circuit breakers. Like AC systems are generally fitted with relays and circuit breakers. Whenever normal current, whenever a fault current occurs there, because of fault, relay senses the fault current. It gives a signal to circuit breaker, and circuit breaker opens the contacts, and it isolates the faulty part from the healthy part. And another method of overcurrent protection is current limiting reactor. A reactor is placed in series with the line, and whenever there is overcurrent because of some fault, it limits the magnitude of short circuit or fault current. So this is overcurrent protection of AC systems. That is about how protection is provided for AC systems, over voltage protection and overcurrent protection. Let us see how we can provide protection for HVDC system. Okay, now we will study how we can provide protection for HVDC system. Now I will write here protection of HVDC system. Just like you provide over voltage and over current protection of AC system, in a similar way you have to provide over voltage and over current protection of HVDC system. So first type of protection that you have to provide is over voltage protection. Now this over voltage protection is, I can write here, similar to over voltage protection of AC system, which you have just now studied a few moments back. Over voltage protection of HVDC system is similar to the over voltage protection of AC system with some difference. Okay, some minor difference is there, with some difference. Okay, we will discuss this over how over voltage protection of HVDC system is provided in a minute's time. Then we have overcurrent protection. Overcurrent protection in HVDC system is not provided by circuit breakers, because we don't have circuit breakers in DC systems, in HVDC systems. So it is provided by using control of valves. So our HVDC system is fitted with controllers, and those controllers control the firing of valves, and with the help of control of valves, overcurrent protection is provided. No doubt we have other methods of overcurrent protection also, like overcurrent protection, we have short circuit protection, we have pole differential protection. We will discuss that later on. Third is, the protection is also provided by some special circuits which are called damper circuits. Hopefully, inshallah, in our next lecture, we will discuss about these damper circuits. And protection against certain maloperations like commutation overlaps is also provided by DC reactor. Okay, we will discuss that later on. Okay, now similarly, then we have these are various types of protections that we have to provide for our HVDC system. We have to provide over voltage protection, we have to provide over current protection, we have to use damper circuits and DC reactor for various other type of protections. Okay, let us first of all study this over voltage protection. Over voltage protection. Before we discuss the scheme for over voltage protection of HVDC systems, we have to see what are the causes of over voltages. I will write here causes of over voltages in a converter station. In a converter station, what are the various causes of over voltages in a converter station? Okay, now if I draw the schematic diagram of our HVDC system, this is the schematic diagram, simplified schematic diagram of an HVDC system. This is maybe rectifier or inverter station, this may be inverter or rectifier station depending upon the direction of power flow. Okay, so this is AC side. Similarly here on this side also you have converter transformer, and then AC side. Now when we discuss the over voltage protection or causes of over voltages in a converter station, there may be various causes of over voltages in a converter station. Maybe number one, due to disturbance originating on AC side. There may be some disturbance on AC side. This is the AC side. Similarly, this is the AC side of your HVDC system. And there may be some over voltages occurring here, some disturbances occurring on AC sides, maybe on this side or on this side, and that will cause over voltage on your DC side. That means that may cause over voltage in your converter station. Okay, this is the first cause. Second cause is due to disturbance originating on DC side. There may be over voltage. The cause of over voltage may be due to some disturbance on the DC side itself. Okay, this is your DC side. There may be some disturbance, some sort of faults, disturbances on the DC side, and those may be responsible for over voltages in your HVDC converter station. And third is due to internal faults in the converter. Due to converter internal faults. Converter internal faults. Some converter internal faults are also responsible for over voltages in your HVDC system. Okay, let us first of all now discuss this. Due to causes due to disturbance on AC side. Causes of over voltages, as you have written here, may be due to disturbance originating on AC side. Now let us discuss what are the various causes of over voltage due to disturbance on AC side. What do you mean by disturbance on AC side? Now various disturbance on AC side may be, number one, there may be switching surges. Switching surges, or what we call as switching over voltages. Switching over voltages due to opening of circuit breakers, due to initiation and clearing of faults. Clearing of faults. Let us suppose a fault has occurred, say a short circuit condition has prevailed. So what will your protective system do? It will start initiation and clearing of fault. Your relay will sense the fault current, it will send signal to circuit breaker, and circuit breaker will open. As soon as circuit breaker opens, it disconnects your faulty system from the rest of the system. And as soon as your system gets isolated, due to high dV by dt, it will result in switching surges or switching over voltages. And that may be one cause of over voltage. In this case, wave front time is greater than 100 milliseconds. Wave front time greater than 100 milliseconds. So this is first disturbance on AC side. On the AC side, initiation and clearing of fault by circuit breakers has taken place, which has resulted in opening of circuit breakers. And sudden opening of circuit breakers means sudden interruption of current, and that will result in high di by dt, LDI by dt voltages, and those are called switching surges or switching over voltages. And these switching surges or switching over voltages are one cause of over voltage in your HVDC system due to first type of disturbance on AC side. Okay. Now next disturbance on AC side may be temporary or dynamic over voltage. Dynamic over voltages due to load rejection. Load rejection in weak AC systems. Weak AC systems. Within brackets I will write here lasting few seconds. your AC system, in your AC system, which may be a weak AC system, which may not be a highly stable AC system, so the load rejection may take place. I mean, suddenly the load is rejected, some load is shut off, some load is disconnected. Okay, because of load rejection, there will be temporary overvoltage or dynamic overvoltage, and this because of temporary rejection of load, there may be overvoltages. Because of load rejection, there may be temporary overvoltages or dynamic overvoltages which may last for few seconds. This is another cause. Third cause is steep fronted overvoltage due to lightning stroke, and the duration is 0.3 to 3 milliseconds. Lightning stroke is a common cause of overvoltage on AC side, and hence it will result in overvoltage on in your HVDC system. Okay, and next is line to ground fault. Again, as I have already discussed with you, a line to ground fault on the AC side will result in raising of voltage of other phases, healthy phases, and this overvoltage will get transferred to HVDC system. So therefore, these are the causes. These are, as I have written here, due to disturbance on AC side. These are various types of disturbances which will occur on AC side, and which will result in overvoltages in your HVDC system, HVDC converter station. Like first disturbance on AC side may be switching surges or switching overvoltages due to opening of circuit breakers. The second is temporary or dynamic overvoltage due to load rejection in a weak AC system. Third is lightning stroke, and fourth is line to ground fault. So this is due to disturbance on AC side. Now, second cause of overvoltage in converter station is due to disturbance on DC side. Let us see what are the various disturbances which occur on DC side and which result in overvoltage in your HVDC system. The first is, again I will write here, steep fronted overvoltage due to lightning stroke. Since your transmission line, DC transmission system, is exposed to atmosphere, anytime steep fronted overvoltages may occur due to lightning stroke. Lightning may strike your DC transmission line, and that will cause overvoltage in your HVDC converter station, in your HVDC system. Second is ground fault on one pole, causing overvoltage of other healthy pole, I should say unfaulted pole. Now one pole, faulty one, there is some problem in one pole in a bipolar HVDC link, and that pole gets grounded, and that raises the voltage of other unfaulted pole. This is other cause. Third is overvoltages due to voltage and current oscillations. We have over last 3 lectures we have studied various types of converter maloperations. One of the maloperation was, if you remember, arc through. The second type of maloperation was misfire, and the third type of maloperation was commutation failure. If you go back, revisit the waveforms which you have drawn when these maloperations take place in your converter, you must have observed that whenever these any one of these maloperations occurs, like for example, if you take commutation failure, this is the normal voltage in a commutation failure when there is no commutation failure. Normal voltage 1.5 times some phase voltage, line voltage, 1.5 times phase voltage, line voltage, 1.5 times phase voltage, line voltage, and suddenly then commutation failure, occurs here. And then this is what happens to the line voltage. So there is certain voltage jump. The voltage jumps from some high value to low value. Similarly, if you draw the waveform for arc through or misfire, similar situation occurs there. There are sudden voltage jumps whenever these maloperations are there. And because of these sudden voltage jumps, in presence of L and C, in your HVDC system, there are inductances and capacitances. Okay, and whenever there is a sudden voltage jump, in presence of inductances and capacitances, there are voltage and current oscillations. Voltage and current oscillations for some time, and these voltage and current oscillations give rise to overvoltages. Okay, so that means the maloperations, converter maloperations like arc through, misfire, and commutation failure, they are responsible for overvoltages in presence of circuit elements like inductances and capacitances. So this is another cause. Next is switching surges, right here. Switching surges originating from AC system transmitted to DC system. Transmitted to DC system. There may be a switching surge on AC system which is transmitted to DC system. Let's see how it will be clear to you with the help of this diagram. Let us say we have bipolar converter system. These are various converters. Bipolar HVDC link with a number of converters in series for high voltage operation. This is ID, this is LD, this is converter output, this is the input to various converters. These are converter transformers. Okay, what happens? Let us suppose there has an overvoltage has occurred on the AC bus somewhere here, and this overvoltage will be transferred on the DC side because converter input voltage suffers an overvoltage. It goes to very high values, and output voltage also becomes very high, and converter output voltage also becomes very high. So output voltage of this converter will proportionately increase with increase in the AC bus voltage. So if there is an overvoltage on the AC bus here, it will result this converter output voltage. So this converter output voltage, let's call it VD1. It will increase. Similarly, VD2 will also increase because it is also connected to same bus. VD3, converter output voltage of this converter, will also increase because it is also connected to same bus, and VD4 will also increase. So therefore we can say that the net over output voltage VD will be, there will be overvoltage due to overvoltage on AC side. Overvoltages due to overvoltage on the AC side are added. So there is overvoltage on AC side. So this converter output voltage also suffers an overvoltage. This also suffers an overvoltage. This also suffers an overvoltage. So all these overvoltages are added. That means multiplied by number of converter groups. Number of converter groups. How many converter groups do we have here? 1, 2, 3, 4. If we had only one converter, whatever overvoltage was here, almost similar overvoltage we would have experienced here. But instead of having one converter, we have here 4 converters. So what is total output voltage here? Total overvoltage. That is the summation of overvoltages. Or if you take overvoltage VD, multiply by number of converter groups. So there are 4 converter groups. So it is 4 into VD1. So therefore it gets multiplied. So that means if overvoltage on AC side has occurred, it will result in multiplication of overvoltage on the DC side by number of converter groups. So a very large overvoltage will occur on the DC side. So this is yet another cause of overvoltage due to disturbance on the DC side. Actually, it is because of disturbance on the AC side which is reflected on the DC side. Next is because of sudden loss of load. Just like in AC systems, in HVDC system also a loss of load may result in overvoltage. And finally, switching, another cause for overvoltage due to disturbance on DC side is because of switching of DC filters and parallel connection of poles and parallel connection of poles. So these are various causes of overvoltages in an HVDC converter station because of overvoltages or because of disturbances on DC side. We have studied causes of overvoltage in an HVDC converter station because of disturbances on AC side, and now because of disturbances on DC side. What is the third cause of overvoltage? Third cause of overvoltage is because of or due to internal converter faults. Internal converter faults. Now, various causes under this group are: number one, due to energization of DC lines. Due to energization of DC lines. Say your DC line was taken out for some repair. Now you have to energize it. As soon as you try to energize it, it may result in overvoltage. Second is due to stray capacitances and inductances. Your circuit may have stray capacitances and inductances, and that will result in overvoltages in HVDC converter station. And third is due to converter faults. Due to converter faults. Various types of faults may occur in your converter station, in your converter, and they may also be responsible for overvoltages in your HVDC system. So these are various causes of overvoltages in your HVDC system. First is due to disturbance on AC side, and second we discussed due to disturbance on AC side, and third due to internal converter faults. What about overcurrents? This was about overvoltages. What about overcurrents? The main causes of overcurrents are, if you write causes, main causes of overcurrents may be overloads and short circuit faults, and these faults will result in, or they are mainly responsible for overcurrent in an HVDC system. But overcurrent is not a big concern. I will write here, overcurrent is not a big concern. Why? Because your classical HVDC systems are based on current source converters. And in current source converters, you have to always maintain DC line current constant. So your controller, whenever there is an overcurrent, your controller very quickly acts, and it always tries to maintain the DC line current or transmission line current constant. We will study that in next module, module number 4, how controller acts to keep your current DC line current, how it maintains the DC line current constant. So, you know, it is for your HVDC controller, HVDC system controller, it is very easy to maintain the current constant. So therefore, overcurrent is not a big concern. What is big concern is overvoltage. I will write here, overvoltage is a concern, and you have to take, protective measures for protecting your HVDC converter station or HVDC system against overvoltages. Now let us try to, I will now show you overvoltage protection. We have studied the causes of overvoltages in an HVDC system. Like overvoltage may be due to disturbance on AC side, or due to disturbance on DC side, or due to converter station faults, converter internal faults. Whatever the cause of overvoltage may be, you have to properly protect your HVDC system against these overvoltages. So let us see how we can protect our HVDC system against these overvoltages. Let me show the overvoltage protection scheme. Overvoltage protection scheme. I will draw the schematic diagram of overvoltage protection scheme. We'll take a bipolar HVDC link. This is our converter transformer. Similarly, these are the converter transformers feeding various converters. Now neutrals are grounded. This is YY connected transformer, this is Y delta connected transformer. This similarly, this is YY transformer, this is Y delta connected transformer. You know why we have two 6 pulse converters, one fed from YY connected transformer, another from Y delta connected transformer. Similarly here we have two 6 pulse converters. One 6 pulse converter is fed from YY transformer and another from Y delta connected transformer. It gives 12 pulse operation. We already know, we have already studied it. Okay, so then you have an AC bus. This is AC bus. And let me show you the protection schemes. Now on the AC bus you have filters, various types of filters, like let me first of all draw, then I will explain. This is AC filter arrestor. We have, lightning arrestors for providing over voltage protection. This is AC reactor arrestor, AC reactor, which is part of filter, AC reactor arrestor. Fine. So we have LC and C and L. This is AC filter on the AC side. Because you already know we have harmonic filters in our HVDC systems. So these harmonic filters also have to be protected against over voltages. So this is over voltage protection is provided by lightning arrestors. This is a lightning arrestor which protects this reactor, AC reactor. So that's what I have written here, AC reactor arrestor. And this is your AC filter, and this AC filter is also protected by this lightning arrestor. That's what I have written here, AC filter arrestor. Then you have a lightning arrestor here. And you have another lightning arrestor here, and these are called this and this. They are called AC bus arrestors. AC bus arrestors. So these arrestors protect the AC filter, and these arrestors, these two, they protect the AC bus, AC side bus. Okay, and then converters also have to be protected against over voltages. Let us see how over voltage protection is provided for converters. It is provided like this. Okay, these are all lightning arrestors. These are all, and they provide protection to these valves. So they are called valve arrestors. I will write here valve arrestors. They provide protection to converter station valves. These converters comprise of valves, so they provide protection, complete over voltage protection to valves. Then you have a valve protection here also. This is your DC bus here, for example. So you have another arrestor here, lightning arrestor. Okay, this is called converter unit arrestor. This is converter unit arrestor. So this is your complete converter unit, and converter unit is also protected against over voltages by this converter unit arrestor. And then you have another arrestor here. This is called midpoint. It is connected to midpoint of this DC bus. Midpoint DC bus arrestor. Okay, fine. Then you have one arrestor here. It is called DC bus arrestor. DC bus arrestor. It protects DC bus against over voltages. Then you have a line reactor, LD, and that LD is also to be protected against over voltages by this arrestor. So this is called DC reactor arrestor. This protects DC reactor against over voltages. Then you have DC filter here. On the DC side also you have a filter, and this is your DC filter, and this is DC filter arrestor. This is called DC filter arrestor. And finally you have a DC line arrestor here. DC line arrestor. So that's all. So this is how your converter station, how your converter is provided complete over voltage protection. Your system comprises of AC bus, and then DC side, AC side and DC side, harmonic filters, and then converters, valves, DC line reactor. All these components have to be protected against over voltages. This is your harmonic filter. These are the harmonic filter arrestors. This is AC bus. These are AC bus arrestors. These are converter valve arrestors. This is converter unit arrestor. This is midpoint DC bus arrestor. This is DC bus arrestor. This is DC reactor arrestor. This is DC filter arrestor, and finally this is DC line arrestor. Now as far as this DC line arrestor is concerned, the problem with DC line arrestor is that it has to, whenever it operates against over voltages, the arrestors also work on the principle of ionization. If you have, for example, arrestor on AC side, when it ionizes, then in AC there is natural zero. At natural zero, deionization automatically occurs. But the arrestor which is used on the DC line, which is called DC line arrestor, that arrestor does not experience any zero crossing, because DC current or DC voltage does not have zero crossing. Okay, so therefore, when the DC line arrestor ionizes, you have to deionize it. For example, if this is your DC line arrestor, see, DC line arrestor, when it operates against over voltage, it provides over voltage to to your DC line, then it ionizes. It has to be deionized. For that purpose, a special circuit is connected across it. What this special circuit does, I will write here. This circuit adds some oscillating current which has natural zeros, required for deionizing of path. So this is a special arrangement which is done for DC line arrestors. Special arrangement. If this arrangement is not done, then if this DC line arrestor operates, it ionizes, and it will remain ionized for normal voltages also. So in order to deionize the path, you add this circuit, special circuit, which adds the oscillating current in this arrestor, and oscillating current has natural zeros, and at natural zero deionization of path takes place. So therefore these are special lightning arrestors. I will write here special LAs, special lightning arrestors. So that is about how over voltage. This is complete over voltage protection of your HVDC system. Now let us see how overcurrent protection is provided. Now since we have studied over voltage protection scheme, let us now study overcurrent protection scheme of your HVDC converter system. Overcurrent protection scheme. And when I say overcurrent protection scheme, you have to provide overcurrent protection against. So protection has to be provided against, number one, overcurrents, that is fault currents or short circuits. Then differential protection also has to be provided. Differential protection between the poles. Say you have positive pole and negative pole. If ground current flows, that means that ground current is because your positive pole current is not equal to negative pole current. That's possible only if some fault has occurred in one of the two poles in your bipolar system. So for that purpose we use differential protection. So in addition to overcurrent protection, We use differential protection also. Let me show you the schematic diagram of a simplified overcurrent protection. We will again take a bipolar converter system. This is your converter by bipolar HVDC link. Now this is AC side, and on the AC side we have circuit breaker for overcurrent protection. And now let us, after the AC side, after some time we will see the DC side. This is the converter transformer. This is another converter. If this is Y-Y connected converter transformer, this is Y delta connected, so that this gives 12 pulse operation, right? Now what we do is we have a current transformer here, and this current transformer provides, it senses the overcurrents, and it gives, whenever there is overcurrent, the sensed overcurrents are given to this block. OCP means overcurrent protection block, and this overcurrent protection block provides the overcurrent protection. Another current transformer is here. This provides VGP. VGP means value group protection. I will come to that. Similarly, you have here OCP, that's overcurrent protection, and next protection is VGP, value group protection. Then you have a current transformer or current sensor here also. This senses the fault current, and it goes here, and it's another input goes to this. Okay, and then you have pole differential protection. This is pole differential protection. Let me show you. PDP, pole differential protection. And this is your DC side. Okay, now what is this OCP? OCP is overcurrent protection. Overcurrent protection. VGP is value group protection. Value group protection. And PDP is pole differential protection. Pole differential protection. If you see in this schematic diagram for overcurrent protection, overcurrent protection on the AC side is provided by these overcurrent protecting schemes, OCPs, and valves are protected against overcurrents by these VGPs, valve group protection schemes. And how is DC side protected against overcurrents, faults? For that purpose we use PDP, pole differential protection. Okay, normally if pole currents, see this plus ID is same as this ID. If there is no fault current, then there is the ground current will be 0. Okay, this ID is same as this ID. The current in two poles will be same, and hence this pole differential protection will be non-operative. It will not operate. But as soon as due to some fault in one of the two poles, say this pole develops some fault, then there is the difference in the two currents, and that difference flows through the ground. So therefore this pole differential protection senses the difference between the two pole currents, and it provides the differential protection, pole differential protection. So pole differential protection provides protection against, it provides, I would like to say, it detects ground fault, detects ground faults, because whenever there are ground faults, the two pole currents will be different, and pole differential protection will provide the protection on the DC side. So this is in fact the main protection, overcurrent protection on the DC side in your HVDC converter system is provided by your HVDC controller, which I am not showing here. By valve control. Okay, the delay angle or the firing of valves is controlled in such a way that this ID is always maintained constant. We'll study that in our next module number 4, HVDC control schemes. Okay, so overcurrent protection is fairly simple. As you can see, overcurrent protection, OCP, valve group protection, VGP, and pole differential protection, PDP. So that's all about some causes of overvoltages, causes of overcurrents in HVDC systems. We have studied the desirable features of protection scheme, And we have seen that protection scheme, when you design the protection scheme, it should be selective in nature, it should be discriminative in nature, it should be fast, but it should not be very fast. Okay, it should be reliable and it should be fitted with backup protection. And then you need to protect AC system also and DC system also, because AC and DC, they are part of your HVDC system. Now, AC side protection means you have to provide protection against overvoltages and overcurrents on the AC side. What are the causes of overvoltages on AC side? Various causes of overvoltages on AC side are, switching surges, and then line to ground faults, and also lightning strokes. And how do you provide protection? By using overhead ground wires, or by these protective gaps or lightning arrestors. Now, what type of protections you have to provide on the DC side? In your HVDC system, in your HVDC converter system, or in your HVDC converting station, you need protection against overvoltages, which is similar to protection against overvoltages in AC system with some minor difference. And you need overcurrent protection also, which is mainly provided apart from overcurrent protection, valve group protection, and pole differential protection. You use the control of valves, firing angle or firing delay angle control of valves to maintain the DC line current constant, to protect your HVDC system against overcurrents. And then you also use damper circuits, and you also use line reactors, which have some other purposes. Of course, they also protect your system against some maloperations. Now, various causes of overvoltages in your HVDC system are due to disturbance on AC side, and due to disturbance on DC side, and due to converter internal faults. Now, various disturbances on AC side may be line to ground faults, maybe sudden load rejection. Okay, it may be because of lightning stroke, or it may be switching surges. Various causes of overvoltages on DC side, I mean disturbance on DC side, which are also responsible for overvoltages in your HVDC converter stations, are ground fault on one pole, which increases the voltage of other pole, unfaulted pole. And then lightning stroke, because your DC transmission line is exposed to atmosphere, and it may suffer lightning stroke anytime. That will cause overvoltage. And then because of misfire, maloperations like misfire, arc through, or commutation failure, there are certain voltage jumps, and these certain voltage jumps in presence of inductances and capacitances cause current and voltage oscillations, and they result in overvoltages. Okay, that means these maloperations are also responsible in converter station overvoltages. And then overvoltage on AC side will originate on DC side, and in fact on DC side, if you have many converters in series, then the overvoltage will be overvoltage of one converter multiplied by number of converter groups. So it will be multiplied by number of converter groups. So the overvoltage on AC side will cause a very large overvoltage on the DC side. And then this loss of load is also responsible for overvoltage in your HVDC converting station. And finally, switching off DC filters and paralleling of DC poles is also responsible for overvoltages in your HVDC converter stations. And third cause is due to converter internal faults, energization of poles, okay, or stray inductances and capacitance, and converter internal faults are also responsible for overvoltages in your HVDC converter station. Then overcurrents are because of faults like short circuits or ground faults, etc., and maybe overloads also. So therefore, you have to provide overvoltage protection and overcurrent protection. Overvoltage, I have already discussed with you a comprehensive overvoltage protection of your HVDC converter station, in which we have seen that various types of lightning arrestors are used for protecting your HVDC converter station. And for DC line arrestor, it's a special lightning arrestor, because in DC line arrestor, to deionize the path, you need an additional circuitry, which is shown by this circle, and it in fact adds some oscillatory current in the DC line, which has natural zeros, and at natural zeros deionization of path takes place. And then overcurrent protection is provided like this. Is a simple schematic diagram for providing overcurrent protection to your converter station. This overcurrent protection comprises of three components. OCP, which means overcurrent protection, is shown here. VGP means valve group protection, which provides protection to various valves in the converter stations. And PDP, pole differential protection, which provides protection whenever there is a fault on the DC side, okay, like ground fault. And apart from this OCP, VGP and PDP, control of converter valves using special control techniques will also always result in maintaining DC line current constant even during these faulty conditions. So this is about overcurrent protection. Inshallah, in our next lecture, we will try to discuss the role of these damper circuits and DC reactor for providing a sort of protection to your HVDC converter station. And we will try to finish our this module number 3 in next lecture. Please go through this lecture and try to study these protection schemes of HVDC converter stations. Thank you.